So how'd it go? What happened to the energy level of the pulse as it traveled down the Slinky? It reflected or bounced off your partner's hand and then died down or dissipated as it traveled back to yours. What about the pulse size when it hit the cup? Did a bigger pulse size contain more energy and knock the cup further? Yeah, it should have. The bigger the pulse, the bigger its amplitude and the more energy it has. How about when you were making the waves? Did you notice a relationship between the frequency at which you were generating the waves and the wavelength? Faster the frequency, the shorter the wavelength. Slower the frequency, the longer the wavelength. So let's connect all of this to the crash avoidance sensors. So how did crash avoidance sensors detect objects? Well, remember what happened to your pulse or a wave when it hit your partner's hand? It reflected off and came back towards you, right? Well, the same thing happens with the sensors. The sensors send out these electromagnetic pulses that travel as a transverse wave out to the objects. Those waves bounce off of the object and some of them return back to the sensor. The sensor calculates the one-way travel time, either out or back, and multiplies that time by the speed of the wave, which in this case is the speed of light. That's how it calculates the distance to the object. Now, the car's computer uses all this information to inform drivers of their surroundings and warn them of any potential collisions that they may encounter. Did you calculate the typical range of the different types of crash avoidance sensors? Which one goes the furthest? Let's take a look. First, let's look at electromagnetic wave sensors, or EM sensors, like radar, LiDAR, or visible light cameras. Each produce EM waves of different wavelengths and frequencies. Each have pros and cons, so engineers usually integrate a combination of sensors to create a comprehensive and redundant safety system. Short-range radar has the shortest wavelength and highest frequency. Next is medium-range radar. Visible light cameras, which work a lot like our retinas, have a little longer wavelength and slower frequency. Long-range radar's wavelength is longer than cameras, but shorter than LiDAR. LiDAR has the slowest frequency, and its wavelength is much longer than visible light. That's why we can't see the lasers. So how fast do EM waves travel? Yep, that's right, they travel at the speed of light. That's around 300 million meters per second, or around 670 million miles per hour. That means those waves travel out and back in less than a blink of an eye. Sound waves are fundamentally different. They travel about 1 million times slower than light waves. It's science, it's engineering, it's cool.